Yeah, thank you very much for the introduction and for the invitation to come here. I would like to talk about rethinking the origin of neutrino masses and how the role of gravity, what kind of role gravity is playing in there. So I would like to present you a very non-standard neutrino mass model with a lot of implications for cosmology and astrophysics, which will be like first half theory, and then the second half may be more interesting for you, but I try to keep it very simple in the beginning on the particle physics side. I developed this model in collaboration with my former PhD advisor, Giyad Vali. This is this first reference down here. And then very recently, I published 2 papers on certain astrophysical and cosmological consequences on neutrino mass bounds from cosmology, on dark energy, and also on neutrino decay from astrophysical neutrinos. So this is what I would like to talk about today. I already gave a talk here at CITA in October last year, but this was a very condensed version just at the Blackboard, so maybe some of you remember. So today this should be a bit more lengthy, and because we're not so many people, you can just always just interrupt me and ask questions as many as you want, and we can keep it very informal if you want. Okay, so let me start with the overall question that we are trying to answer. So the question is, why do we have this huge gap between the neutrino masses and the masses of the other fermions in the standard model? This is widely seen as unnatural, so people assume that the neutrino masses are not generated through the conventional Higgs mechanism and that we need some kind of beyond standard model physics to explain those masses. So what people usually do is they develop a new model at very high energy scales, which becomes manifest in the very early universe. For example, the seesaw mechanisms or models involving large extra dimensions. So all of these models are getting manifest at like GeV or much, much higher energy scales, which become important in the early universe. And in those models, the neutrino masses are connected in some or the other way to the Higgs mechanism. So it's assumed that we get a mass from the Higgs condensate at this electroweak symmetry breaking scale here, and then we have some new beyond standard model physics effect that suppresses those masses. For example, in the seesaw mechanism, it's a very heavy right-handed Majorana neutrino mass that's suppressing the mass that we're observing. And for large extra dimensions, it's just a very tiny overlap of the wave functions of the right-handed neutrino living in the higher dimensional bulk and the left-handed neutrino living on the 4-dimensional brane that we are observing. So we would like to take an alternative direction and go to the late universe. So even beyond the specific model, I think this is a very interesting approach because we are able to show that new physics effect can't only be hidden at very high energy scales, but also at very low energy scales. And they can also efficiently decouple from the standard model processes that we are observing in the universe. In our model, we are not adding any new species or any grand unified theory groups or anything on top. What is usually done in those models, also no extra dimensions. We're just taking the standard model as it is, and we're coupling it to gravity. And we see that there's an inherent source of neutrino mass generation coming from the gravitational side. And this is connected to a theta term in gravity. I will explain to you on the next slide what this means. At this point, I just want to give you a very broad overview how the model is built up. So in the presence of this theta term, neutrinos are condensing in the very late universe. This gives rise to effective neutrino masses, and all of this is generated at a new energy scale which is inherent to gravity. So we have an additional scale on top of the Planck scale, which is the well-known scale of gravity. And this new infrared gravitational scale turns out to be numerically coincident with the scale of dark energy, which is very interesting because we're here connecting many different phenomena like neutrino masses, the dark energy scale, gravitational physics, and we even developed an axion model which fits very well into this framework. So I would like to give you a very brief overview of the model itself. So we had this question before, now we're calling QCD for help. So that means that we're taking QCD as an analogy, just to give you an intuition for the model itself. So maybe you're not very well familiar with those physics. I try to either remind you or to keep it very simple by introducing those new concepts. I think this is very educational to just look at the facts that are very well established in another theory. So in QCD, we know that there is a so-called theta term. This is the term that I wrote down here. It's just proportional to the gluon field strength and the G tilde, which is the epsilon tensor times the gluon field strength. We have a free parameter theta here, which is an angular dimensionless parameter, and we have a lot of other constants here that I omitted. So this is a very famous term in QCD, which for a very long time was thought to be irrelevant, because this GG tilde is a total derivative. And every time when in a Lagrangian we have a total derivative, we can just integrate over the Lagrangian and then the derivative goes away. So people thought for a long time that this is just a mathematical artifact and this has no physical meaning at all, until Toft, Witten, and Veneziano showed that there are actually effects, non-perturbative effects, which means they're not captured in perturbation theory, that make this term physical, even though this is a total derivative. And those terms are connected to the vacuum structure of the theory, and there's something like tunneling solutions and other semi-classical and quantum effects. And these effects are actually physical in the sense that they give rise to physical phenomena that we have measured. And the most important phenomenon is the mass of one of the mesons of QCD. And because this is going to be very relevant for our model, I would like to briefly remind you of where these mesons are coming from and where this mass is coming from. So the mesons in QCD, the pions, the kaons, and the eta meson, they are coming from a symmetry breaking process. So in QCD, we have three very light quarks. We have the up quark, the down quark, the strange quark. They have light masses. So we can approximately treat them as massless. And then we have a flavor symmetry. So it's U3 because we have those three particles. It's a vector times an axial symmetry. And in QCD, we know that in the early universe, a quark condensate is forming and is spontaneously breaking this symmetry down to that symmetry, which gives rise to the mesons of QCD. So those mesons are the Goldstone bosons of the symmetry breaking, and we have 1 plus 8, because this U3 symmetry here that is broken contains a U1 part, which gives rise to this eta prime meson, and an SU3 part, which gives rise to those 8 other mesons. Now, the puzzle was for a long time why this eta prime meson is so heavy, so much more heavy than these 8 other mesons. And the resolution are actually those non-perturbative effects. So exactly those effects that nobody realized that they're existing and that they're making this term here physical. These effects, so this GG tilde term is appearing here on the right-hand side of the divergence of the current. This is the current of this U1 symmetry. And this U1 symmetry is the symmetry that is broken to give rise to the eta prime meson. And that this current here is not conserved, so that there's no zero here, but there's this expression GD tilde, means that this U1 symmetry is anomalous. So it is spoiled by those non-perturbative effects, and this gives rise to a very large mass of this eta prime meson. Yeah, so this is essentially everything you need to know about the analogy. There's just one last thing, namely that this vacuum correlator here can be one-to-one related to the condensate of quarks, which is responsible for breaking this flavor symmetry. So you don't need to understand all the details behind of this. The main essence, the main message to take home here is that these effects are very well established in QCD, and we showed that they can also appear in different sectors beyond QCD. One thing that many people don't know is that not only QCD but also other theories contain theta terms, and one of these theories is actually gravity. So this term here was already written down many years ago, many decades ago in the 80s, and the term is very similar. We have a free parameter theta g. R is the Riemann tensor, R tilde is the epsilon tensor, times the Riemann tensor. And this term exists in gravity, but just as in QCD, we don't know whether it is physical or just mathematical. So what it means is that this term here is a total derivative, just as in QCD. So we are standing in front of the same question as people did in the QCD case. We don't know whether there are non-perturbative effects that make it physical or not. And the final answer to this question will be given by a full theory of quantum gravity, but we don't have it yet. And there are a lot of clues that the term actually exists. So it's a huge debate in the quantum gravity community. People like Stephen Hawking were strongly in favor of it. Other people were strongly against it. So it depends on your UV completion of quantum gravity. There are many solutions, gravitational tunneling solutions in the vacuum, but it's unknown from a theoretical side. So what we did is we took this as a starting assumption that the term exists and tried to see what kind of consequences this has for the standard model. So we took the opposite approach. We said we don't know theoretically whether the term exists or not. So we see phenomenologically what kind of consequences does this term have for cosmology, for astrophysics, for particle physics experiments, and then see whether we can actually falsify the existence of this term or maybe even verify it. And the mathematical tools that we are using are mostly taken from these papers here, 3, so by Guy Advali, Jackie Pai, and other people. And it's basically that we have chiral anomalies in both of these theories. So this is this anomaly that I was talking about. We have it in gravity as well. This is something very well established. There's no discussion about this, unlike here for the theta term. And if this theta term actually exists, it was shown in those references here that the topology structures, so the vacuum structures of the two theories, are very similar. And also we get massive pseudoscalar bosons in those two theories. And this is something I will explain more in detail. So now we are considering gravity to coupled minimally to the fermions of the standard model. So this is something we can very easily do without making additional assumptions. And we're considering the lightest fermions of the standard model. These are the neutrinos. So we have 3 neutrinos that we treat as massless at the moment. And we can treat them analogously to the 3 lightest quarks of QCD. And then we see if we have 3 massless neutrinos that they will be the ones mostly affected by this anomaly. Just as previously, the lightest quarks were the ones mostly affected by this anomaly. So we were able to show that in case that this theta term is actually physical, we can derive exactly the same equation as in QCD by using this mathematical framework developed in this reference 3. And we're able to show that in the presence of this theta term, we can get a one-to-one correspondence between the physicality of this expression and a neutrino condensate. Of course, we don't know yet at which scale this happens, so this is just a mathematical relation of those two quantities. However, what one observes immediately is that if we have a condensation of neutrinos and we start with 3 massless neutrinos, then this is going to break flavor symmetries, just as in QCD, where we had the 3 light quarks and the flavor symmetry got broken by the quark condensate. We here have a flavor symmetry as well. So we have 3 neutrinos, they have a flavor symmetry, and this gets spontaneously broken. And this gives rise to bosons in the neutrino sector. And we have a few more bosons than in the QCD sector, because in our case, this symmetry gets broken further than in the QCD case. So these bosons are similar to the mesons of QCD. The mesons are quark-antiquark bound states. You can describe them as those. And our bosons are neutrino-antineutrino states coming from breaking the symmetry. So this is the way how the model is built up. Just to give you, again, the way of the arguments that we're taking. We're starting with these non-perturbative gravitational effects. They have to be either quantum or semi-classical, because in the classical theory, you can just simply integrate away this term in the Lagrangian. This then gives rise to this theta term, to its physicality in pure gravity. And this one single assumption leads immediately to the existence of a new energy scale in the system, a fundamental new energy scale. And this scale is similar to the QCD scale. So the QCD scale is the scale where the quark condensate gets formed, and in our case, this would be the scale at which the neutrino condensate gets formed. And it is a priori a free parameter, so we can't predict the exact scale in the theory. The only theoretical expectation that we have about the scale is that it should be strongly suppressed with respect to the Planck scale. So either power law suppressed or exponentially suppressed, because non-perturbative effects, something like tunneling solutions, they're always exponentially suppressed with respect to the cutoff scale of the theory. Later we will see phenomenologically that this scale is actually in the infrared regime. It's something between milli-electron volt and electron volt. But as I said before, as long as we don't know what kind of non-perturbative effects make the term physical, so as long as we don't know what kind of underlying quantum gravitational theory we have in the universe, we can't predict the scale. So we have to treat it as a free parameter here. So this is pure gravity, and now we can couple this again to the neutrino sector, or to the sector of all the fermions in the standard model. The neutrinos are just the only ones that get strongly affected by those effects. So if we couple gravity to the neutrino sector, as I said before, we get this effect of neutrino flavor symmetry breaking by means of this anomaly. This gives rise to a neutrino condensate exactly below this infrared symmetry breaking scale. And this gives rise to our 1 + 14 ghost stones. And this eta nu is very heavy, just as the eta prime in QCD, which was this puzzle historically. And these 14 additional ones are actually massless. And now...
So neutrinos interact with a weak interaction with all these ghost stones. Bosons interact with interaction.
Yeah, but because it's so low energy, you will decouple from every high energy process you have. So if you go to high energy model building, you're always suppressing your beyond standard model effects by dividing by the high energy scale. And here, conceptually, it's a very different approach, because all the new physics effects, they are suppressed in high energy processes because you have a low energy vertex. And this is effectively dissolving in every high energy process.
I'm just wondering,
so
now are these things going to be interpreted as neutrinos, the 14?
So they're interpreted as kind of neutrino mesons. So you have neutrino, antineutrino bound states. Yeah. So, and of course, they will, just as neutrinos, interact weakly with the rest of the standard model. But because the interaction is so weak, and all of the emergence of those ghost stones happens, we wouldn't have noticed them. They completely decouple from most of the processes, but not from all of them. So this is interesting, where we can see some cosmological and astrophysical effects there. Now, the most interesting consequence of this one assumption that we have, the theta term in gravity, is that this generates neutrino masses. And we're not making any additional assumption here. This is something which is well known in QCD. So in QCD, we know that the quark condensate is contributing to the quark masses. This is something which is not so much discussed, because one always discusses the Higgs mass contribution. But the contribution from QCD exists as well. And this is what we have here. So we have an effective mass contribution coming from this neutrino condensate, which only emerges after the symmetry breaking. And before that, the neutrinos are massless. And this coupling, so I try to depict it here. So I don't know if you're familiar with these kinds of diagrams with the condensates and this weird blob in the middle. So what it tries to say is that we have neutrino condensates here. These are the blue blobs. And then we have the non-perturbative interaction in between. And here we have two free neutrino legs. So we have nu bar nu. And this right-hand side is effectively the mass term that we get for the neutrino in the Lagrangian. And this in QCD is called the 't Hooft vertex. So as soon as we have a theta term and we have this anomaly, which we have in our model, then this vertex is just built in. So there's no additional assumption there. Now you might ask whether we can allow for a neutrino mass hierarchy, because we know that gravity couples equally to all the fermions in the standard model. So why should we have different masses from gravitational effects? And the reason actually is that the mass hierarchy is determined by a spontaneous symmetry breaking effect. So the masses are proportional to the condensate that is generated. And even though gravity couples equally to the different flavors, we are, by minimizing this effective potential that we can write down of all the order parameters we have, which are becoming, after the condensation, the neutrino mass, the neutrino condensates, sorry. In this case, we can actually generate a neutrino mass hierarchy. But because it's a spontaneous symmetry breaking effect, we could have all kinds of different mass parameters. We could have equal masses, hierarchical masses, no masses. We could have everything. So we can't predict the mass pattern, but we know the masses phenomenologically. So this is something where we have to, again, go back to pheno. The last interesting theoretical aspect that I want to share with you is that the mechanism works for both Dirac and Majorana neutrinos. So a lot of mass models only work for one of those possibilities. And on the previous slide, I have shown you in all the equations the Dirac case. So maybe if you're familiar with the symmetries I showed to you, they are apparent in the Dirac case. But in the Majorana case, the entire argument goes through as well. We just have less symmetry to break, and therefore less Goldstone bosons. But the mechanism itself just goes through the same way. And this will become interesting for astrophysics because we can actually find a way to distinguish Dirac from Majorana neutrinos from astrophysical data, which is something I want to talk about later. Okay, so this is the theoretical part of my talk. There were not a lot of formulas because I thought if you're interested, I can just write them on the blackboard or you can just come to me later and ask. So if there's some questions, maybe you can ask them now or later.
Well, the reason it works for Dirac and Majorana is because it's gravity.
Yeah, yeah. So, and these anomalies are the same for Majorana and Dirac particles, yeah. Yeah. And then, of course, the condensate would look different. So it wouldn't be nu bar nu, but there was like nu, C, nu, and yeah, so, yeah. Okay, so then I would go over to the cosmological consequences and the astrophysical ones, and if there's some time left, also particle physics consequences. The first thing on the phenomenological side, what we have to do is we have to look at different constraints on the symmetry breaking scale, lambda g. As I said before, theoretically, we just know it has to be strongly suppressed, but we don't know where exactly the scale should be. But it turns out that on all the scales of the universe that are possible, something between 10 to the minus 33 electron volts to 10 to the 28 electron volts, so the entire universe, all the scales that we have, there's only a very little window where the scale is still allowed to happen, to be existent. So we're starting with an assumption, just to simplify these arguments. We're assuming that the energy scale of the condensate and the energy scale of the flavor symmetry breaking is equal to the temperature in the universe where the phase transition happens. We know in QCD that these scales, these three, they can be parametrically different. So there could be factors of pi, there could be like order 1 to 10 differences, but of the order of magnitude, all of them, we are assuming them now to be equal, just to show you the different constraints we have on lambda g. So let us see where lambda g is still allowed to exist. First of all, we have a very strong constraint coming from standard model physics. We already mentioned this a little bit because of the weak interaction and the QCD interactions. If the scale lambda g were very high, we would get this condensation and other physical effects everywhere in the standard model, and this would screw up all of our precision measurements. So just for example, we would get a contribution to the core condensate that would be of order of the QCD scale if the condensation would happen there. And this is something experimentally ruled out. So we know that the scale has to be very strongly suppressed with respect to standard model scales. Then we get an upper bound from cosmology. And the reason here is that the neutrinos are self-interacting due to those new effects, which is ruled out in the very early universe until photon decoupling. Because, we get the shift in the CMB peak. So we know neutrinos are free streaming in the early universe, and this is up to a temperature of approximately 0.3 electron volt, which is the temperature of photon decoupling. And then we get a lower bound, which is only like 2 orders of magnitude lower than that. And this is coming from the neutrino mass splitting. So we know that the heaviest neutrino at least has a mass of 50 millielectron volts. So this is experimentally known from those mass differences here. And we know from that this condensate scale, because it can maximally couple with 4 pi, to the neutrinos, we get that at least this scale has to be 4 millielectron volts. But as I said, again, the temperature where the phase transition happens could be lower. So all of this is just parametrically equal. And this actually means that we have this phase transition at any point between photon decoupling or today. So the today's temperature is 0.2 millielectron volts. So it could happen at any time between photon decoupling and today. And we can't theoretically make a prediction when this happens. So another lower bound we have from gravity measurements. We have very precisely measured gravity up to millimeter distances, which is this entire regime down here. So millimeter corresponds approximately to inverse millielectron volts. So the first thing we see here, what is very interesting, is that we started with a free parameter and we constrained this parameter to be very close numerically to the scale of dark energy. So dark energy, the density of dark energy is 3 millielectron volts to the power of 4. So we see that we have a numerical coincidence here, which has been noted previously. So neutrino masses and dark energy, they're at the same energy scale, and everything else is not. So this is a long-standing puzzle, why this is the case. And of course, we can't say here why the cosmological constant problem exists, what is the solution to this problem, because we can't say why the Higgs condensate doesn't contribute to the cosmological constant, why the quark condensate doesn't contribute. So we can't resolve the cosmological constant problem here, but we can note that we have a neutrino vacuum condensate, which is exactly at this energy scale. And this will become important later. So now let me come to the first very concrete prediction that the model has. And this is actually the prediction which makes it possible to falsify or verify the model in the very near future. And this prediction is that the cosmological neutrino mass bounds become very strongly weakened or even vanish completely. And the reason is that the neutrinos don't have any masses in the standard model, as we know. This is the neutrino mass problem. So the neutrinos are massless in the very early universe all the time until this phase transition happens. And then due to this symmetry breaking, due to this phase transition, the neutrinos gain their masses. And immediately afterwards, the neutrinos are decaying into the lightest neutrino mass eigenstate. I showed you previously that we have those Goldstone bosons, and with these bosons, the neutrinos can decay from the heaviest to the lightest eigenstate by an emission of one of those bosons. I will show you the process on the next slide again. So the neutrinos decay into the lightest eigenstate. So this means, first of all, cosmologically, we can only get access to the lightest eigenstate, but then the crucial point is that neutrinos and antineutrinos are actually annihilating away into these new bosons. And because most of them are massless or have really tiny masses that are cosmologically negligible, neutrino masses can't be tracked in the universe. So we start with massless neutrinos in the early universe, then they become massive for a very, very short amount of time that is cosmologically not resolvable, and then they decay and annihilate away into dark radiation. So the bottom line of this is that these conventional neutrino mass bounds that we have that are, like, depending on who you ask, like 0.2 or 0.12 electron volts, these bounds are not applicable anymore, and neutrino masses could still be as large as up to 6 electron volts, like the sum of it, what you cosmologically consider. And the reason is that the only bounds that we have that are not cosmological are the ones from beta decay experiments. And these bounds are on the electron neutrino, and the bounds are 2.2 electron volts currently, but they will be improved very soon. So this is something where the model can have very interesting consequences, because there's this experiment currently running. They promised to publish the first data on the masses this year. Maybe it will be next year, let's see. We've been waiting for a long time for this experiment to get some data. But this experiment can probe the masses from 2.2 electron volts for a single mass down to 0.2. And this is exactly the regime where from standard cosmology we wouldn't expect to see anything, because this regime is already ruled out by cosmology. But in our model, this is still allowed, so Katrin could actually see a very large neutrino mass. And as far as I know, there's no other model that could give such high masses. Of course, the bounds can be weakened if we are modifying lambda CDM or the neutrino sector, but like such a substantial weakening, I don't think that it works in other cases. Now what we looked at as well is the impact on other cosmological parameters. This is a project that we've done last year, so in collaboration with Christiane Lorenz, Erminia Calabrese, and Sten Hannestad. We looked at other cosmological parameters because there are these discrepancies between early and late time measurements of cosmological parameters like H0 or sigma 8 and many more. So we thought maybe we could resolve some of these tensions. Yeah, so the result is not so very encouraging, unfortunately. So the H0 discrepancy, I haven't shown here anything because it just stays the same. There's just no difference at all. And so for the sigma 8 tension, what we have here is just a broadening of the different contours. So we see that almost everything stays the same apart from the Planck C and B contour. This gets broadened, and we see if we take into account that we have one new degree of, like, not a new degree of freedom, but one new parameter in our simulations, we see that we have a slightly better fit, but not really significant. So we see that there's not really a huge difference. But what is interesting to take home here is that this phase transition could be a first order phase transition. And in this case, we are stuck in the wrong vacuum for a very long time. So first order phase transition means we're stuck at the point where the neutrinos are massless for a long time. The universe is supercooling. So we have a huge amount of false vacuum energy for a long time in the universe. And eventually we can tunnel or roll away from this false vacuum, and we get a huge release of this false vacuum energy density into the neutrino mass sector. And this is something that I've plotted here on the right-hand side. So we looked at the cosmological constant parameter at the density, and we see that for a very large neutrino mass, we have a very large amount of false vacuum energy density. This false vacuum energy density behaves as a cosmological constant until the phase transition, and then it decays away. So we see that if we have a very large mass, then the additional cosmological constant that we assume to be there out in the universe, which is assumed to be at 0.7, the density parameter of it, this becomes substantially less because we have a huge additional contribution coming from the neutrino sector. And this is also the reason why we have this degeneracy, like this broadening up of the plot here, because we see that the dark energy density in the very late universe after this phase transition is substantially reduced due to the decay of this false vacuum, and all of this is released into the neutrino sector, which first is the sector of dark matter and then transforms into dark radiation. But this is a step that we didn't consider in the simulation. So this means that omega m could, at least in those simulations, was much larger than compared to lambda CDM. Now you might ask the question, why do we have a cosmological constant at all? Because we have a false vacuum energy which is compatible, or at least giving a very large contribution to the dark energy that we observe. So why shouldn't it be the entire dark energy, the entire cosmological constant that we observe? So this would be a possibility, and it's very strongly constrained. So if dark energy is simply the false vacuum energy of this neutrino phase transition, which could be possible, then this phase transition must have happened extremely recently. So at a redshift of 0.2 or even smaller, so very, very recently. This was something worked out by Wiley and collaborators a few years ago. But this is something, because Wiley already worked it out, we haven't gone into this detail here. But this would be quite exciting. So we would actually be living in a local patch of the universe where we don't have any dark energy anymore because we just tunneled away out of this wrong vacuum. And we're now in the true vacuum without dark energy and with a huge possible neutrino mass in our universe. So this is one possibility, that it's a first order phase transition. It can also be a second order phase transition. It's depending on this effective potential that I talked about 2 slides before. And in case it's a second order phase transition, the cosmological consequences wouldn't be so drastic as here. But the first order one, of course, is cosmologically more interesting because it can be probed very soon. And we already get strong constraints here. Okay, so now you might ask the question, what happens if we're adding new stuff on top of the standard model, which is something that particle physicists do all the time. So they're considering sterile neutrinos, they're considering asymmetries between neutrinos and antineutrinos in the universe, just as the baryon asymmetry. So what happens in our model if we are adding extra things to the standard model? So the first thing is if we have sterile neutrinos. These are very well motivated by anomalies in experiments. So in short baseline experiments, we have anomalies that are hinting towards the existence of additional neutrino species which are not active but sterile, and they have masses of order 1 electron volt. So they're different anomalies, they're not really compatible, but many people favor the sterile neutrino solution. However, it's ruled out by cosmology, at least according to standard cosmology, because it screws up the cosmological neutrino mass bounds, and it screws up the number of effective degrees of freedom in the early universe. In our case, these discrepancies would be resolved because the light sterile neutrinos, the mass bounds are gone, as I said, just due to annihilation and decay. And on top of that, the number of effective degrees of freedom is unchanged because the sterile neutrinos are decoupled from the rest of the standard model in the early universe. Because the neutrinos are massless, and the only way to couple active to sterile neutrinos is by the mass, and this is turned off in the early universe. Then the question is, what happens if we have more neutrinos than antineutrinos in the universe, or more antineutrinos than neutrinos, just as the baryon asymmetry? Here the point is that not every neutrino finds an antineutrino partner to annihilate if there are less antineutrinos. So in this case, we would have an excess of neutrinos in the universe, and we would have, after the annihilation, we would still have relic neutrinos left over, because not everything annihilates. And in this case, these leftover neutrinos, they're clustering. Not only gravitationally clustering, as they just do, the relic neutrinos, as we know, but on top of that, due to these new interactions that we have, they're clustering even more, especially locally, which would be important for the Ptolemy experiment, because this Ptolemy experiment that tries to measure the relic neutrino background would then have an enhanced rate of detecting them, and would also be more sensitive to these larger masses that we are predicting. Okay, so this is the cosmological part. If you have any questions about it, just feel free to ask me about it. Yeah, so we looked at these weakened mass bounds, at the consequence for dark energy and the possibility to have a decay of dark energy. And this clustering project is still ongoing work in collaboration with Lena Mirsagoli, so I can't say much about that. But if you don't have any questions, I would go over to the astrophysics part. Let me check how much time I have left. Oh, yeah, 10 minutes, so not too much. Okay, but there's not much more I want to say. On the astrophysical side, the most exciting part is a part that I already mentioned. So it is neutrino decay. We know that neutrinos can decay in our model, the heavier neutrinos into the lightest one. And these decays are different depending on the Majorana or Dirac nature of the neutrinos. If we have a Dirac neutrino, then a neutrino can decay into a neutrino. An antineutrino can decay into an antineutrino, but this process here is not allowed because it would violate lepton number to have a neutrino going into an antineutrino or vice versa. So we have different decay channels depending on the nature of the neutrinos. And first of all, one important consequence is that all the neutrinos that we observe on Earth that come from very far away have all decayed on their way to Earth. So if we look, for example, at ice cube neutrinos or supernova neutrinos, they're all in the lightest mass eigenstate until they reached Earth. And this is a very distinct feature, something that is searched for at ice cube, for example, because we would have a very distinct flavor pattern. We know the mass eigenstates, the lightest ones. I mean, we don't know whether it's nu1 or nu3, so it could be two different possibilities, but we know the flavor composition of those. We know, for example, in a normal neutrino mass hierarchy case, we have predominantly electron neutrinos in the lightest eigenstate. And this is something that can be checked. And yeah, we need more statistics. That's the bottom line of the current data that we have. We don't have enough to say anything. But one thing where those decays will become important are if there's a nearby supernova exploding soon. and also in solar neutrino data. So we know the sun very well and the processes in the sun. We know what kind of spectrum we are expecting. We know that neutrinos are not decaying, the ones from the sun. So this sets a lower bound on the lifetime. We also know that atmospherical and reactor neutrinos are not decaying, so we have a lower bound here. But our prediction is actually at the edge of what we know from solar neutrinos. So this is like the maximum traveling distance before the neutrinos are decaying. And this becomes very interesting if we look at Majorana versus Dirac, because if we have this decay, then we get different energy distributions for the Majorana and Dirac cases. And this is something that I've been exploring until very recently with Georg Raffelt and Eduardo Vitaliano. We saw that the energy distributions for the strongly hierarchical case and for the degenerate mass case are strongly dependent on whether we have Dirac or Majorana. So if we can measure this distribution, we can distinguish those two options. So here you can see the orange curve. This is the Dirac scenario of neutrino into neutrino. On top of that, in the Majorana case, we have this blue curve, which is neutrino goes into antineutrino, and they're adding up. And they're also different depending on the hierarchy of the neutrino masses, because if the secondary particle is much lighter than the initial particle, then we can just neglect the mass and we just get this very simple box. But in the other case, the energy distribution would be shifted. So this is an interesting conceptual consequence of these decays. And the thing that we can look forward to in the near future is that for the solar data, we have only measured neutrinos and not antineutrinos, because the sun is mostly emitting neutrinos and just a very tiny little amount of antineutrinos that we can't detect so far. So if we have an antineutrino detection from the sun, then this requires some kind of conversion of the neutrinos into the antineutrinos. And this is something that, at least in our case, would reveal a Majorana nature of the neutrinos. Conversely, because we haven't seen any antineutrinos, we can place very strong bounds on the Majorana case. So currently, the Dirac case is favored over the Majorana case just because of that, because we don't see any antineutrinos from the sun. Because these couplings in the Majorana case, they would be already constrained to 10 to the minus 4, which is already very small. Yeah, so I think this is quite exciting to see that one can distinguish the nature of neutrinos even beyond the standard approach of neutrino-less double beta decay. So far, this is the only approach that's known, and we have added here an additional possibility. Okay, so let me check. I have another 5 minutes. I have another slide, but maybe I shouldn't go too much into the details. So if you're more interested in the details, you can just ask me afterwards. So just very briefly, I would like to mention that this theta term is giving rise to different polarization intensities of gravitational waves, because this R tilde term is coupling. It is known in the gravitational sector as a Chern-Simons term. Maybe you've heard of Chern-Simons gravity. In specific regimes, it also is relevant for the CMB, which is not the case here. But for gravitational waves, we get different polarization intensities because we get a kind of birefringence effect when the gravitational waves are traveling through this non-trivial topological vacuum background. On top of that, we get a new, we called it gravity competing force, so a force similar of strength to gravity in very short distance measurements, something like millimeter experiments, so torsion experiments where we try to measure the Newton's law. And this is something we predicted in a follow-up paper that I mentioned already that can solve the strong CP problem with this setup. We called it a domestic axion setup. I don't want to go too much into that detail, but this gravity competing force is specifically happening in this setup because we get new forces just between hadrons, which is non-trivial because we're coupling our gravity sector. We're not only considering the neutrinos, but also the lightest quarks of the standard model there. On top of that, we know that these bosons that we have, these 1 + 14 new bosons, they are axion-like particles. So they are pseudoscalar particles that are coupling also to light, to electrons, very strongly suppressed, but they're coupling to this. And here the interesting message is that astrophysically, these processes are very strongly suppressed because of this argument that I said in the very beginning, that in very high energy and high temperature environments, this vertex is just dissolving. So it's a low energy vertex. But in experiments like shining light through walls, so we have an incoming photon, we have an axion-like particle going through a wall, and then an outgoing photon. In this case, in this setup, which is a low energy setup, these bosons can actually appear. And the interesting thing here is that usually nobody expects a signal here, because the signal, the coupling, the strength that we need to get a signal here is already ruled out by astrophysics. But in our case, the astrophysical constraints don't apply to the model. So in our case, we could actually get a signal here, but not in the astrophysical environment like the sun. So here, there is another interesting experimental thing going on. And finally, I just wanted to point out that we get any kind of flavor violating processes, not only in the neutrino sector, which are just the neutrino oscillations that are violating flavor, but we can get flavor violating processes that are currently searched after at LHC, at mu2e, at a lot of experiments that are also affecting the more massive fermions of the standard model. And as far as I know, these processes, they usually come from high energy scales, and we're actually the first people who try to explain this from a very deep, low energy origin. Okay, so I'm going to wrap up now. My summary is that we just started with this one assumption. So we have gravity, we know that there's a theta term, just as in QCD. We just don't know whether it's just a mathematical artifact that we can integrate away, or whether there are non-perturbative effects that make it physical. And there are strong theoretical arguments for and against it. So we assumed it exists. And we were able to point out that if gravity gets minimally coupled to the fermions of the standard model, this leads to fermion condensation. And fermion condensation is ruled out on all energy scales, and all the effects are ruled out on all energy scales, apart from the infrared scale, milli-electron volt to electron volt, which is the scale where the neutrinos are the only particles that are affected by this physics. So we showed that this yields neutrino condensation and effective neutrino mass generation, and it's independent of any high energy model, like Higgs mechanisms or seesaw mechanisms. And it works for both Dirac and Majorana neutrinos. On the phenomenological side, we showed that large neutrino masses are still allowed by cosmology, because cosmologically we can't track those masses. So this is something where we could, in the very near future, see a discrepancy. For example, Euclid doesn't observe any neutrino masses, even though they're expecting to see those, then there's something going wrong. And this would be a possibility to explain this. And on top of that, I talked about the possibility of having a substantial fraction of dark energy to decay in the late universe, or even the entire dark energy to decay after this phase transition. And on the astrophysical side, I talked about enhanced neutrino decays, and there were many more things that we explored. So we explored possible signatures at the Scattering experiment, the beta decay experiment, at IceCube, that measures this flavor composition of the astrophysical neutrinos. And we looked at many more things. So if you're interested, you can just ask questions now, or come up to my office. I'm in this visitor office in the 14th floor until tomorrow morning. Or you can also just read through those two papers. These are the latest ones. There are also two earlier ones from the model building side. These are more phenomenological. Yeah, or you can just ask me now. So thank you very much for listening, and if you have questions, just ask them. Thanks.
Okay. Any questions? I have a question. Okay, go ahead. Just wondering, so now that we're observing gravitational waves, like light
LIGO and so on? Have you thought about trying to constrain this sort of model by looking at this chair side and stuff?
Yeah. So it can be constrained, the scale in general, if you look at the different polarization intensities. Because so in the first run, this was impossible because LIGO had the arms aligned in the same way, so you couldn't measure the polarization. But with Virgo, that's added. It's now in principle possible to constrain the scale. And this is something people have looked at, but the constraints are very weak. So this is conceptually interesting that we get this different polarization intensities. But for testing the model, yeah, like this would be far beyond what we have. It's several orders of magnitudes below. So
Even with like the deluge of objects that they're
yes, even now. Yeah, just because the distance at which the arms are operating, it's not large enough. Yeah. Yeah. So it's not about the number of like the number of events you're measuring, but of the distance that you can probe with this. No. So I think with like the current or even the planned ones, I don't think it's possible. Yeah. I find it conceptually very interesting that you have this effect, which is coming from this coupling through the anomaly from this R tilde term to the neutrino sector. But yeah, this is more just theoretically interesting, but experimentally, this is more the line to go to with the cosmology and astrophysics. Yeah.
So there's a bunch of things that would be evidence for this effect. Is there, so with any of these measurements, is there a way to rule this idea out if we don't like, are any of these things strong enough that we should definitely be seeing it at some point?
So I think if Euclid or other cosmological surveys in the next 5 to 10 years, I think that's the time scale. If they find neutrino masses cosmologically, I would say the model is ruled out. So it's always possible, as I said, we could have these asymmetries between neutrinos and antineutrinos. And in this case, neutrinos are not completely annihilating away. But this is an extra thing that can't be predicted by the model. It can just be added. And so if it's on the level of baryon asymmetry, then we have a factor of 10 to the minus 9 of the neutrino density that's left over, and we can't see it anymore. Yeah. So this would be the best way of ruling it out. Yeah. So Katrin can't rule it out because we can't predict whether the mass is 2 electron volt or maybe 0.2 or maybe even lower. So Katrin can like just provide a hint into this direction, but the cosmological surveys, they can rule it out. Yeah.
Does this have any impact on, I think it doesn't have any impact on the cosmic neutrino background relationship to Big Bang synthesis, since this is too low an energy phenomenon. But what about on oscillations generally? That it would mix all the flavors together at a pretty efficient way?
Yeah. So just because it is the origin, like is the proposed origin of the neutrino masses, we just get the flavor oscillations as in this standard case. Yeah, and these wouldn't be messed up by this because we get the masses that we generate. But so this new physics, the bosons, they're not. They're giving rise to a decay of these eigenstates, and of course, if you're decaying into the lightest eigenstate, you don't have any oscillations anymore because you're in a mass eigenstate. In the lightest one, but at least from the distance scales we know to the sun, this effect is not happening. So this will affect neutrino oscillations from supernova neutrinos that are coming to Earth or from ice cube neutrinos. But apart from that, there are no consequences there. Or did you mean like a different regime or?
Well, I was just wondering whether we could try to think about it in terms of the context of what we're doing with the cosmic neutrino background and Big Bang nuclear synthesis, but I don't think that...
No. So for, so in the very early universe, this doesn't change anything. It's just that in the very early universe, the neutrinos are massless, which means that a lot of constraints on the neutrino sector don't hold true that usually people infer from the early universe. For example, with the asymmetries, we have very strong constraints on electron neutrinos versus anti-electron neutrinos from BBN. We have very strong constraints on that. And usually people say, okay, this also holds true for the tau and muon sector because we have masses and they're mixing. And in our case, this is not true. So we have weaker constraints. So this is one example. But neutrino masses in the early universe don't do much apart from that. So we don't really change anything there. We can't.
Oscillations do play a role.
Yes.
Can play a role.
Yes.
So
Yeah, they usually, in the standard picture of having like a seesaw mechanism or anything, they play a role also already in the early universe. In our case, the neutrinos are massless until the very late universe after photon decoupling, and then the neutrino oscillations will start to play a role, yes, because then the neutrino masses will get generated. And for the relic neutrinos, they then annihilate away, so this will have an impact on measuring the background, because you can't measure the background anymore at Ptolemy, for example, if all the neutrinos are annihilating away. You can't measure the cosmic neutrino background anymore because it's just gone. Yeah, unless you have this asymmetry that I mentioned. So I think these are the main effects that we have in our case. Okay.
All right. Well, let's thank our speaker again.